not web accessibility because you already talked about that. But I want to talk about search on the web. Actually, especially for the IMM students, and I think also for the lifestyle informatics students, there is a course on information retrieval in the minor year 3. But because there's 2 reasons why I want to tell you about this. Because search on the web is important to understand how the web works and how the web actually is something that you can use, and not just a big bunch of pages that nobody can access. So from a web technology part, it's important, but it's also important because of some of the methods that we'll show, some of the metrics to measure things are actually also used in all kinds of other courses and in other fields. So it's good to have an introduction into these things, and you will learn more about those later in your studies. Yeah, and also today after the lecture there will be I think a practical where you actually play around with these some of these examples and information retrieval measures. Okay, so this is web search. Okay, so what we'll talk about today is search engines, specifically web search engines, but we'll talk about them also in a more general fashion. So what do they actually do behind the scenes when you do a Google search or a Bing search? How do they work? But also how good are they, right? So what does good mean in this case? What can we use to evaluate these type of tools? And through this we'll also talk a bit about some of the information laws that you need to be aware of if you want to make a good search engine. Okay, so first of all, what is a search engine? So there are more than one search engine. You might not know this, but there's actually not just Google, there's also others. And there have been a lot more. So Alta Vista search engine, I'm not really sure if it's still up and running, but it used to be the most popular one on the web before Google came along. The Yahoo search engine was very popular. So there's all kinds of web search engines that claim to be generic search engines over the entire web, right? And we'll see what that even means later on. But more importantly, what is search actually? And how can we look at search? So we look at it from an information retrieval perspective. So information retrieval, the task of getting the right information for the user, is a task and a set of tools and technologies that is way older than the web. So what web search is basically just information retrieval on the web. Right? So information retrieval is the activity of obtaining information resources, so documents, but can also be images or whatever, that comply with some information need. And this information need is in the head of a user. And you get it from a collection, from a corpus.
Another related question. Will today's lab be mandatory?
Will today's lab be mandatory? I think all labs are mandatory.
Because a lot of people, like all trains are cancelled and stuff, and people can't.
Yes, so we'll deal with that. But in principle they're mandatory, but if today you don't make it, I'm sure that will be less punishing about that. But you guys are fine. So. But of course your lab partners are not. Okay, good question. Okay, so back to the information retrieval. So what we like to do is look at this from a sort of structured perspective, to look at how search engines work, what they do from a sort of a model perspective, and this is the classical information retrieval model. There are others, there are updated ones, but this actually still works quite well if we want to talk about different concepts in search. Right, so this is also one that you I hopefully saw in the paper about search, in the broader paper, the taxonomy of web search. So they explain this model and what all the different parts there are. Right, so we can talk about information need. This is where it all starts. So the information need is something that is in the head of the user. Right, so this is, I want to know X, or I want to see Y. And then the query is the way that the user actually presents it as input to the system. So that's only where the system starts. So the top is basically not a part of the system. Right? So in the classical information retrieval model, the query can be a textual query, like the one you would post to Google, but it can also take all kinds of other forms. It can take a natural language sentence, so you can ask what is the tallest mountain in the world, or I can just Google tallest mountain. Those are slightly different forms of the query, but they might match the same information need, right? So I might just want to know what the tallest mountain is. Queries can also take the form of images. If you do reverse image search, which Google allows you to do, and other search engines as well, the input is not a search string, but an image. right? So this model still holds, but you have different types of queries. And you might have different types of queries for the same information needs. You might have different information needs that result in the same query. So these are not always completely linked. Right, so and then you do some magic, and that magic then retrieves the relevant documents according to from some corpus, right? So from some body of knowledge. It can be a body of images, or it can be the web, right? So this is the first thing. It can be from the web, which is what web search is, retrieve things from the web. But it can also be from a library, right? So before the web, if you remember, there were libraries, and you can actually go to the library and try to find the book that is relevant for you. And then you had a system, and then you can enter your information, your query that hopefully matches your information need in some system, and then the system will look it up in their index. Right? So again, the same model holds whether you do it on the web or not. And then what happens is, so hopefully you get some of the results from the corpus, and then the results are presented to the user, and then the user can say, well, actually I didn't mean bank in Amsterdam, I mean bank to sit on in Amsterdam, or like a international bank in Amsterdam, right? So by providing feedback, there's a sort of this feedback loop that allows users to refine their search query to eventually find their information need. Right? So this is the classical model, and we'll get back to it once or twice further down the line. Okay, so what kind of information need, what kind of queries can we have? So the information needs, if you look at the taxonomy of web search article from Broder, there's 3 that are listed: navigational, informational, and transactional. So who can give me an example of a navigational query?
Maybe like Google Maps.
Google Maps, what do we mean? So that's a system?
Searching.
Yeah, okay, so it's a very literal navigation. It's not even that wrong, but a navigational query is a query that you use to navigate from one space to another space. So I know where it is, I know where the information is, I just use the query to go to that specific place, right? For example, I Google Twitter. Instead of entering twitter.com, I Google Twitter, I take the top hit, and then I go to the Twitter page, not because I want to know stuff about Twitter, but because I want to navigate to this specific part, right? So navigational in that sense. So informational is when I do want to know about Twitter. So I enter stuff like Twitter stock price, right? So now I don't want to know, in the end I want to know what the Twitter stock price is, probably. So that's my information. I don't want to go to pages that list stock prices. They might have the answer, but my information need is in this sense informational. And then finally, they have transactional queries that match transactional information needs. They don't really give you answers or point you to the right directions, but they do something, right? So that we know from the JavaScript lectures that the web is also a set of applications, or provides a set of applications, and queries might actually trigger things that do other things. So, for example, do queries or actions in Google Maps, which then trigger something down the line, so that you get a mail later on, for example, right? So this is to distinguish these 3 types of queries. All right. So when looking at queries, there's all kinds of different queries, but like I said, the images and natural language queries. But the ones that are most popular and most easy to talk about are so-called Boolean queries or Boolean search queries, which basically are expressions of terms that are searched for, so textual terms, that are separated by words and or and not. Right? So look, they're here, and or not. And even if they're not listed explicitly, they might be listed implicitly. So if you Google for Twitter stock prices, it will search the interpretation of that query is I search for a thing that has both Twitter, or has Twitter, stock, and prices on it. And so it's interpreted as an AND query. And if you want Google to not interpret it as an AND query but as an OR query, you just put OR in between the things and it finds different results. Right? So this is a Boolean search query. And also we're talking mostly about ad hoc queries. So these are queries that are one-time queries rather than elaborate, sort of getting closer to the information needs through this feedback loop. And so this is the standard type of information retrieval query that most systems tackle and are evaluated on. Okay, so there's all kinds of queries that are not ad hoc. So we've seen some, or it might not be Boolean. Right, so for example, browsing. Browsing is information retrieval behavior that might satisfy an information need, so it might still match this, this model that I've shown you, but it's not Boolean query, right? So for example, I want to know something about the height of the tallest mountain. I go to Wikipedia and I go to mountain pages, and then I try to browse to the right answer. Right? So in this case, I still have the information needs, I still have the system, but I get to my final answer in a different way. There's all kinds of social bookmarking things that I actually might house the answer for me, and I might navigate it in specific ways. And there's very popular now recommender systems that try to answer your question before you've even formulated it. Right? So Netflix, for example, it thinks that you always want to know what next to watch. And it's right all the time. And the same for Amazon.com, right? So it thinks, if you're on my site, you probably want to know what cool book you want to read. Right? So it actually will just provide you answers from a corpus, right? Documents from a corpus that might match your unformulated information need, unformulated query. But again, we can still look at those from the same model. A very popular way of getting to the right information from a corpus is through facet browsing or filtering. So we're not going to go too much into detail, but this is really sort of a combination of browsing and recommendation and applying filters. For example, if you're going to eBay, right, and you want to buy a set of headphones, then you can make all kinds of decisions. Like I want to restrict it by brand, or I want to restrict it by color, or I want to restrict it by price. And through this, you start with the corpus, and then you separate it, and you select different subsets until you get to a finite small subset that you can actually look at, and you buy the one that matches both your needs and might be the cheapest, or the one that looks nicest. Right? So this is another way of, again, information needs, interacting with the system, not through ad hoc Boolean queries. Okay, so thinking about ad hoc Boolean queries, right? And you can imagine that Google and other search engines deal with millions of those per second. So how do we do this? How does Google work when you do a query that nobody else has done before and still give you the answer in a quarter of a second? Right? So there's all kinds of tricks. So they have a bunch of servers. You've probably heard about this. Right? Google bought a new server park, and it's somewhere in the Arctic because then they don't have to pay for cooling. And so there's real power behind this. So this is one answer. So they're good because they have large things, but that's not the only answer. Right? So indexing is the answer that we're going to look at. So there's smart ways of doing this lookup, of finding your answer in this big bunch of documents. But they also do all kinds of smart things, like they do pre-selection, so they know the type of queries that you're likely going to ask, and they might sort of prioritize them, the lookup in their systems. We're also not going to talk too much about those, but there's all kinds of tricks that make it really work. But we'll look at the more fundamental tricks of indexing in the next slides. Okay. So does the search engine actually look up the results live on the web? So you do a query, does it go on the web and go to the first page it sees? And then I see nothing. No, it's not. Right, so you can imagine that would be an answer, right? So let's say I have 10 documents. I enter a query, like Brutus, and I go, is it in the first word? No. Is it the second word? No. And then I just go through all of my documents, and then once I find it, I say, oh, I find it. Right? So that's maybe the naive way of programming this, and it doesn't work, right? So you have to travel all over the web. Every time someone does a query, that's super slow. So no, it doesn't do that. So then does it just save the entire web on a big hard disk and do the same, but just look up documents, but instead of having to do the HTTP request every time, it just does it on disk. So this is smarter. You lose the HTTP traffic, but still it's too slow. Right? So this doesn't work. You have to go through each document every time. And with billions of documents, that will take a lot of time. So no, that's also not what happens. So what does it do? So it makes an index. Right? So all the search engines use indexes, and this is a word that you've heard about before: the Google Search Index, and Bing Search Index. So what is an index? So the index comes from these old things which are called index cards, and they were used actually to identify information in other corpora. So libraries use these and actually are still being used in some of the older institutes in the Netherlands to identify all kinds of information that they have. Right? So you write down on index cards what is the content of some larger content, like books, for example. Right? And then now you only have to go through the index cards, so that's a bit easier. And you order them alphabetically or by date, so it makes it easier to look at information. And index cards actually come from the index finger, so they have the same etymological background. So just really to point at things and find it. Right? So this is why the Google index is called index. Okay, so not all pages are included, duplicates and junk are removed. So this also is sort of a efficiency thing, but that's really not what makes it work. But this index is the okay. So let's go build one. How do we do it? And how does Google index the web or other search engines? So, okay, so there's the three main steps, and we'll go through them in the rest of this lecture. So 1 is crawling, 2 is pre-processing, and 3 is actually building the index and finding a good data structure to do that. Okay, so first of all, we need to know all the web pages, right? So if I had a book of all the web pages, it would be great, but I don't because it's every time it's updated, and it's a big book, and that's actually the index, right? So how do we get it? Okay, so let's say I build a site about how horrible this course is, or I don't know, I make something about my cats. So how do I know? How does it show up in Google in 3 weeks? Right. So what Google does, it doesn't know all the possible IP addresses / something in the world. So what it does is it uses the stuff that you've been building, namely the links, to identify pages in the big network. Right? So what it does is crawling is really following these links. So actually, what it will do is it will take a page, look at the A tag, the link tag, and then follow the href and see what's there, and then take another page. And so this is the linking, the crawling part. It just follows the links that are there. So it uses the HTML code to identify this. So just in video form, let's see if this works. So this guy was quite successful in doing this. So this is Sergey Brin.
I think you've been on before, right? Yes.
Google's Sergey Brin.
If you're going to build a search engine, is to have really good fun corpus to start out with. In our case, we used World Wide Web, which at the time was significantly smaller than it was today. But it was also very new and exciting, and there were all sorts of unexpected things there.
So the goal for the first 3 units of the course is to build that corpus. And we want to build a corpus for our search engine by crawling the web, and that's what a web crawler does. What a web crawler is a program that collects content from the web. If you think of a web page that you see in your browser, you have a page like this. And we'll use the Udacity site as an example web page. So it's got lots of content, it's got some images, it's got some text. All of this comes into your browser when you request a page. The important thing that it has is links. And what a link is something that goes to another page. So we have a link to the frequently asked questions, we have a link to the CS 101 page, there's some other page. And that link may show up in your browser with an underscore, it may not, depending on how your browser is set. But the important thing that it does is it's a pointer to some other web page. And those other web pages may also have links. So we have another link on this page, maybe it's to my name, we can follow to my home page. And all the pages that we can find with our web crawler are found by following the links. So that won't necessarily find every page on the web. If we start with a good seed page, we'll find lots of pages. And what the crawler...
Right, so this is a key term. He says it might not necessarily find all the pages on the web, but maybe if we find a good seed page, then we will find a lot. So this is actually what happens. You get a few seed pages, and then you crawl the web, and you hope that you find everything, but you really don't. Right, so this is what happens, and you can do this for. I'm not sure if you got this in your programs yet, but you can do this depth first or breadth first, right? So you can first consider all these pages, build a list of one step deeper, and then go one step deeper, or you can dive in it and really go all the way. Of course, they use a mixed strategy here. Okay, so this is what the crawling does, and this is what the Google bot does, right? So there's a Google bot that visits your page. So if your cat page has 2 visits, it's probably you and the Google bot. And it does it to make sure that your page can be indexed. Right? So it's nice because it then shows up in the list. If it has incoming links, right? So that's a must-have. So often, if you have a WordPress account, then you already get all kinds of incoming links from the central WordPress server. So there's all kinds of things that make this work. But if you don't, then you need to make sure that you have some links pointing to your page. Otherwise, nobody will ever find it.
So if you have nothing linking to your page, then it won't show up in Google.
Exactly. If you set up your own server with your own IP address, you put a page cats.html, it will never show up in the Google search engine. And we'll see where it ends up later. Okay, so if you don't want your page to be found, you can actually do that, right? So if you have a super secret cat page, you can actually set in your on your server, you can set a robots.txt, and it's commonly understood. That means please don't visit these pages and don't index them, right? So if for any reason you have some information that you don't want everybody to find, you can actually list it in your robots.txt document. So it doesn't mean that it's not possible. So any malevolent crawler can still do it. There's no technical way that you can block a robot to do this, because it will just pretend like it's a browser and it will do this. But the Googles and the Bings adhere to this agreement. So again, I think this is an interesting case because you see here that it's not just a technical thing; it's also a social thing. Right? So this is nice for people that don't want their pages to be indexed. Technically, it's not enforced. Okay, so to answer your question, so can you actually crawl? Do we get the whole web? And by the way, how big is the web anyway? Right. So one of the nice things is, okay, so can we get the web? No, but what we do know is that the web is not a homogeneous set of links. So we actually know that there are pages that link to a lot of other pages and get a lot of inlinks. These are so-called hubs. And these are pages that people like to link to and link from. So, for example, Wikipedia or the Yahoo directory or things like this. Right? And choosing these as seed pages is a good idea because then you immediately have a lot of outgoing links and incoming links that you can actually follow. Right? So this is a nice thing if you want to crawl the web, that you can use these hubs. So you're sure that you don't end up in these endless crawling activities, and in 1,000 links you still are finding new pages, right? So you know that the web is not that big in diameter. Right? So I think the average size between 2 pages is something like 15 links because of these hubs. Okay, so that's a nice thing, but still you won't get it. And this is what we call the deep web. Right? So this is where your secret cat page ends up. So the deep web sounds super freaky, and this is also the part of the web where you get your illicit drugs and armor. So this is where that happens, the Tor stuff happens. But really, what the deep web means is just a non-indexed web, right? So this sounds immediately a lot less nefarious because your secret cat page lives here. So basically, if you look at what Google indexes is the tip of the iceberg, and there's all kinds of unindexed pages, which are, for the majority, very uninteresting. So these are pages that are, are generated, for example, right? So if you look at eBay, they might generate pages based on what's in their database, and not all the generated pages, because there might be infinite amounts, right? I used this headphone with this color background for this specific user, that might have a different URL. Then not all of those URLs are always indexed. Right? So it is important to know that the deep web is not just where the drugs happen, but also just where unindexed pages end up. And it's way larger. We don't know how large it is because we can't index it. Right? So this is not crawled at all. Alright, so back to the question, how big is the web then? So we can maybe guess. So this is not easy to identify. There are a few people trying to do this, and all these numbers are super funky and they might fluctuate a lot. So who can guess the number of websites on the web in 2013, right? So 5 years ago. So does anyone want to do a guess? No. 30 million? Yeah, okay, so, okay, we'll just remember, you remember 30 million, right? Okay, so let's see, maybe you know this, the number of pages that are indexed by Google. So this is the number of web pages, and not websites, but pages that can be found, you know?
400 million.
400 million. Right, so, okay, so the take-home message is that we really don't know that well, but these are sort of estimates that we know. So, for example, the total number of websites on the web, so the estimate in 2013 was 760 million. So it's just, you know, ballpark, okay. So let's say that's correct. So live websites, whatever that means, so this is a website that's, the top number is websites that apparently the researchers knew about, and about 5 out of 7 of those is actually responding, right? So this is the magic of the 404 error. So it's fine if about a third of the web breaks. It's still fine. So a guess was that at that point, that 14 trillion web pages were actually live. So this is based on the average number of pages per site, and you do sort of calculations. You get somewhere. But basically, all those are super big guesses because this is the deep web stuff that we don't know. So what we might know, at least, we don't know, but Google knows, is how many pages they index. And they've been, so first of all, there was, let's say, 10 years ago, there was a race between Microsoft and Google and Yahoo, telling everybody how many pages they were indexing. I'm indexing 10 billion pages, I'm indexing 15 billion pages. So at the end, they stopped doing that at around 50 billion, right? So Google now says, or doesn't even say it anymore, but people estimate that they index, or have in their cart index around 50 billion pages, and Microsoft Bing is 14 billion. And you can wonder if it matters, right? If the important pages are in those missing 30 billion, or if those are all unimportant, or maybe less important categories. Right, so this is the size of the web, but again, you should take this with a grain of salt because it might be completely different. There's a Dutch guy who did research on this on the World Wide Web size. He basically reports these index sizes. So you can have a look at that and see the live number. Okay, so so we can actually see that it also grew a lot. So this, I always like this graph. It starts in December 1990, so around the web. So this is the first website and the second website, and etc. etc. And it ends in August 2007, so way before the actual sort of the hockey stick went up. And what I always like is this one. So this is when the web turned out to be a bad idea. So right, we always thought, oh, this is a super good idea, and then it crashed horribly, and everybody thought, oh, this web was nothing to begin with. We abandon ship and just go back to paper books. Right, and at the time it looked really scary. It was like a real crash, like for the Bitcoin people, like the one we had yesterday. Right, and if you now look back at it, and this is not an endorsement of Bitcoin in any way, but if you now look back at it, it was really just the minorest of minor dips. Right, so we can see that the number of pages has been growing and growing and growing and growing, and it's probably still growing. Right, so it got really big in 2005, let's say, and that's when search engines became necessary. Right, before this, I started using the web, let's say here, and you could just sort of go to startpagina.nl, right, where all the start pages were, and then you can just go, I want to know about the transportation information. You just go there, and there's the information. Right, so that only works if you have a couple of hundred pages in the Netherlands, let's say, but it doesn't work if you go up to 180 million pages and your information is somewhere on there. You need search engines for the web to work. So that's why they're an important part of the technology that makes this something that is actually usable. Okay, so back to the drawing board. So we're still going through the index. So now we've crawled the web, right? So we have identified all kinds of pages. So we know what's out there, but we don't know what's on there. So that's what we're going to do. Web browsers use standard natural language processing technologies to identify what the web page is talking about. So first of all, it throws out all the HTML tags that you've worked so hard to put in. So sorry about that. But that's not the content, right? So the content is actual text. So maybe it's smart. Alright, so then it does tokenization. So it does some smart things. So it splits up the words. So it takes all the white spaces, all the commas, and all the dots, and it splits them up and identifies all the words. Then it removes words that are meaningless, like I or the or it. Right, so these are called stop words. Usually that's a smart thing because you get rid of a lot of those. A lot of data gets thrown away. That's not really that informational. And then often they do what's called stemming. So this is a natural language processing trick where you look at a word and you take the stem, the stem in Dutch. Right? For example, cars and car are both normalized to the word car. Right? And you can imagine that for search it doesn't matter if the word cars appear or if the word car appears. So this is what typically is done, not always, but most of the time. Walking and walks are normalized to walk, right? The stem of the word. Right, so then now we know about what type of things the page is talking, and we do this for each document, and then we end up with a list of terms. So this is the things that the document talks about for each document. So that's nice.
If they remove the HTML tags, what is the use of the strong and emphasized tags?
Yeah, so that's a good question. So the question is, if they remove everything, does it use interesting information like strong and maybe headers or stuff like that? So the quick answer is, yeah, they don't. So often they don't know what the page is talking about. But the more elaborate answer is yes, they actually do. So what they sometimes do is they give the words that are in between these things a slightly higher number. So this is like a simplified version in that sense. For example, you can put meta tags in the heading. That was what people used to do a lot. And so you say, well, actually my page is about this, and this is what I put in the heading. It's not shown to the user through the browser, but it's only used for this indexing part. Yeah, it's a good point. Okay, so now we have pre-processed documents. So this is an example of pre-processing. There's all kinds of other tricks that can be done, but this is, let's say, the most basic and generalizable one. And then we start building the index, right? So what's the index? So there's a couple of different types that you can build indices, and the simplest one is a term document matrix. So let's say that I have a document. Let's think about the data structure. So a simple one might be I have tuples document word, and I have a super long list that says, well, I have word 1 on document 1, word 2 on document 1. All the words from document 1 are listed, and then I start with document 2, I have word 1. Right, so now my task is I have a query. I look if it matches the first tuple, the second tuple, third tuple. I have to go. It takes a long time, right? It's faster than doing the lookup for each document because I don't have to process the whole document, but only these identified terms. But still, it takes a long time. Okay, so that's we're doing better already, but we can do a bit smarter. So we can build a matrix, right? So it's a better data structure to do this. And now we're going to the Shakespeare examples. So these are the same examples that are used in the article. So you can read along or read this back later on. So a term document incidence matrix is something that you can build, which is actually a matrix where you list all the terms on one axis and all the documents on another axis. Right? So instead of having a long list, you actually have a matrix where you put a 1 if the term appears in the document, and you put a 0 if the term doesn't appear in the document. Right? So this means that the word Anthony appears in Antony in Cleopatra, in Julius Caesar, but not in the Tempest, not in Hamlet, not in Othello, but it does appear in Macbeth. Right? So this is the way that you can read this document. Okay, so that's nice, and now we can have a query. So this is a Boolean query, right? I want to know my query is Brutus and Caesar, but not Calpurnia. So my information need is probably something like give me a play that talks about Brutus and Caesar, but I don't mean the one that talks about Calpurnia. Okay, so that's nice because we can actually represent this as we can actually take the vectors of each of these terms. We just look them up in our matrix. And then what we know for each of the terms is where it occurs. And then we can do a bitwise AND procedure. So we just calculate if all the things are 1, then it's a 1. If 1 is a 0, it's a 0. Right? So let's try to do that. So what's the bit vector for Brutus? Let me see. I hear 1 1 0 1. 1 0 0. Yeah, exactly. So it's Very good. It's just this line, right? 110,100. And what's the bit factor for Caesar? Next one, yeah, so it's 110,111. So what's the bit factor for not Calpurnian? Yeah, I think you're correct. I didn't hear completely, but so it's the bit factor for Calpurnia is 0, 1, 0, 0, 0. But the reverse, the complemented bit factor is exactly the other way around, right? So I can go like this. So it's 110100 and 11. And if I just go for the first spot, it says 111. So the end operation results in a 1. This is 110. So no, that's a 0. So it becomes a 0. So you end up with this this bit factor, and this represents all the documents that match your Boolean query. Right, so it's a very simple set of operations, and it results in this is the result of the query. Right, so the answer is Antony and Cleopatra and Hamlet. That's the answer to the query. Right, so this works. This is nice. You just do a bunch of lookups in your table and you're done. So that's quite cool. But we're not really there. So this is not how Google does it. Why not? Well, it's because we're not talking about Shakespeare, but we're talking about the web, right? And Shakespeare was pretty cool, but the web is even cooler, and it's bigger. That's so if you just take 1 million documents, right? So we know that that's nowhere near the size of the web. But if you take 1 million documents, and we estimate that each has about 1,000 words, which is really not that much, right? So then we get let's do an estimate about how many terms there might be. So a good estimate, and we'll look at how we get to these estimates. But let's just say for now that there are 500,000 distinct terms. So think terms that appear at least once within these 1 million documents with 1,000 words. All right, so now we end up with a term document incidence matrix that is 500,000 times 1 million. Right, so the terms times the documents. So this is a huge matrix. So it says half a trillion numbers, either 0 or 1. But the problem is, or the thing is that we are actually representing a lot of empty space. So most terms do not occur in most documents, of course. Right? So this is a very sparse matrix, like roughly 1 in 1,000 as a 1, and the rest is 0. Right? So there's a lot of information that is lost. Right? So you can imagine that there's about 1 million ones, so that we have a sparse matrix. So we can ask ourselves, what is a better representation? So the answer is, and this is the thing that we're going towards, so we only record the 1 positions. Right? So that's smart. We don't throw away important memory space by recording the zeros. Okay, this is what inverted indices do. An inverted index is basically what all the search engines use as their main component of their search engine. Okay, so let's again go back. So what is an inverted index? It's basically just for every term, you record all the documents for which it does appear. So all the ones. Right? So we say Brutus appears in document 1, 2, 4, 11, 31, etc. We do this for all the terms, and we order them in some way so that it's easy to look up. And now I can actually go through this document, to this data model file. Okay, so how do we build it? Just go back. So, so first we have text, then we still do tokenization, all kinds of linguistic stuff like stemming, etc. And then we just build this inverted index, right? So this is just a repetition of the things I showed you just before, how you get to an inverted index. Right, so this is again, if you have these 2 documents, then you will end up in a big list, and then you convert that list to a document index. And what often happens, but not always, is that you record frequency of the term in specific documents. Right, and we'll see why you will need that later on. Right, so you get this nice postings list, or this list of documents where certain words occur. Okay, so you might think, that's super smart for Google, but of course inverted indices are basically the thing that we've been using all along, right? If any book with the back of the book index, that's basically an inverted index, right? So it has a term, for example, corpses, and it has actually a document, or in this case pages, where that term occurs, right? And they're ordered in a certain way that for you it's easy to find the right pages, right? In numerical order. So this is just, we've been doing this all along, and now it turns out that's also a smart way to do search engines. So inverted the name is a bit confusing. So inverted index is basically just an index, right? So yeah, that's exactly the thing. So it's not an additional layer of magic. It's basically just that thing. Okay, so you know this stuff already if you ever read the book. Okay, so I'm just going to quick look at my timer. This is exactly time for a break. So this is how these inverted indices are built. What we'll look at now, after the break, is how can I can actually measure where something works well, and what other tricks are used to make sure that you get the right answers on top. Right? So we'll see you in 15 minutes. If you go outside, try not to get blown away.